Hi class, this is the last section of our textbook. So just as an overview, what we're going to do is we're going to talk about Hermitian matrices. So basically what we're going to do is we are going to classify three types of matrices. And then we're going to talk about how to diagonalize these matrices in the complex inner product space. Okay, so first we're going to discuss what's called unitary matrices. Okay, so if you remember at the end of the last video, we talked about a unitary space. A unitary space is a complex inner product space. So a unitary matrice, matrice is a matrix that lives in a unitary space or a complex inner product space. Okay, so we classify these in a certain manner, right? So our definition is that if A is a square n by n matrix with possibly complex entries, okay, then A bar, the complex conjugate of A, is found by taking the complex conjugate of each entry of A, right? So again, the complex conjugate of a matrix is you're just conjugating all of the imaginary complex elements inside of that matrix. Okay, the conjugate transpose is called A star. Okay, this is a very important matrix. We're going to talk about it a lot in this section. So the conjugate transpose, so you'll see in a second, I'm kind of jumping ahead a little bit here, but you can find this two ways. Okay, either you transpose and then you conjugate, or you conjugate and then you transpose. Either way, you're going to get the same thing. The order that you do them does not matter, but the A star is the conjugate transpose of a complex matrix and a complex vector space in product space, right? So A star is A bar transpose, or the complex conjugate transposed, or you transpose and then take the complex conjugate of A transpose. Okay, so again, these two things mean you're just doing the same thing but in different order. Here you conjugate first and then transpose, or equivalently, you transpose first and then you conjugate. Okay, it's just very important that you understand the notation. Again, these are equivalent to A star. Okay, and I'm going to mix these up. I'm going to go back and forth between using this form and using this form, just so that you get used to the idea that they're the same thing. Okay, so let's do an example. Okay, if this is my matrix A, if I want to find A star, okay, so what I'm going to need to do is either transpose this first and then take the complex conjugate, or take the complex conjugate first and then transpose. I think it's easiest just to take the complex conjugate. So remember, the complex conjugate means that you change the sign on everything that is imaginary. Okay, you leave the real parts alone. I don't know why, but it's a very common mistake for students. They just change the signs everywhere. You change the signs everywhere, that's you taking this matrix and turning it into negative A. We don't want negative A, we just want the complex conjugate. So this will be 2, negative A, negative I, negative 4I, 1 plus 3I, negative 4 minus I, 2 minus I. Okay, again, if you need to review your imaginary numbers, chapter 6.3, we had a review for the first half of that video on the way that complex numbers work. Adding, subtracting, dividing, multiplying, all that kind of stuff, right? Looking at them as vectors, things like that, moduli. So first thing I'll do is I'll find A bar, because it's the easiest thing to do. So again, I'm just negating the imaginary parts, okay? And then if I take the transpose of that, that is my A star, right? So I change the signs on the imaginaries, and then I flip it about its diagonal, okay? Its major diagonal. Or you can think about it as this first row turns into the first column, right? The next row is the next column, last row, last column, right? In case you forgot how to transpose. So that's what we have, okay? So let's go over a theorem, okay? So say A and B are complex matrices that are n by m. So again, they can be squared, but they don't have to be. C, a complex scalar. Then for our A star, we have properties that A star star will give me back A. So again, this is like saying A transpose transpose. It's just how we transpose in the complex vector spaces, right? A plus B star is going to be A star plus B star. So that's nice, right? That the star will distribute across matrices, okay, for addition. For A B star, you're going to reverse the order, and you can start each independent matrix, right? So, or vector. So A B star will be B star A star. And our last one is I have a complex scalar against my matrix, and then I star that. I can pull out the complex conjugate of the scalar and multiply that times my transpose, and those will be equivalent, okay? Or my star transpose, I guess we would say. Some textbooks will use a small dagger symbol here instead of a star for the complex conjugate. I'm sorry, for the complex transpose. And when I say a dagger, it looks like a funky little cross. And again, that's just standardized in certain textbooks. Okay, I think they also use the dagger for other notations, for other symbols. I think it's a common physics symbol when you're doing things like quantum mechanics. Again, so I always refer to applications. These last two sections are the real applications towards quantum mechanics for everything that we've done. So everything that we've been doing in the real space has really been setting us up for how to do stuff in the complex space. And quantum mechanics literally is just these last two sections, right? Everything you need to do in quantum mechanics is really based on this idea of complex inner product spaces and these unitary matrices and these diagonalizations that we're going to get into towards the end of the section. Okay, so let's go over a couple of properties of these unitary matrices. Let's see. So a matrix that is square and complex is unitary if A inverse is the same as A star, right? So that's our definition of a unitary matrix. So A star has to be the same as the inverse of A. So this is analogous to when we have an orthogonal matrix in the real vector space. And we were able to say that A inverse is equal to A transpose. So if you remember, I believe it's in the QR factorizations, our Q matrices that were orthonormal, we had the property that A transpose was the exact same thing as A inverse. Okay, so now our unitary matrices have these same sort of properties, but in the complex space. So the things that we're able to do, those QR factorizations and SVDs, for example, we can start to do in the complex world, okay, with these unitary matrices. So our next property we have is that, again, if A is complex n by n, is going to be unitary if and only if the columns of A are orthonormal. Same thing here. The only way for this to work was when our matrix was orthonormal. And in this case, with respect to the complex dot product. So we know that there's several ways to define an inner product. And the standard dot product, Euclidean dot product in R, is analogous to the complex dot product in our complex inner product spaces. So here, again, this has very important properties. It's the common inner product for complex vector spaces. So if our columns are orthonormal with respect to this, then we can say that our matrix is unitary. So let's look at an example. Let's show that this matrix here, A, which has complex entries, right? 1/2 plus 1/2 I, 1/2 minus 1/2 I, 1/2 minus 1/2 I, 1/2 plus 1/2 I is unitary. If you notice, this looks symmetric, okay, so far. Although if we try to do A star, it's not necessarily going to be the same thing, right? Because we'd have to conjugate everything and that'll give us different values. But we're trying to show that it's unitary, okay? So I can try to find A inverse if I wanted to, okay, which is fine, and show that that's the same thing as A star. So I could find A star and then find A inverse and compare those two. So that's one thing to show that this is unitary. Or what we're going to do now is I can show that my column vectors are orthonormal, so that this is a length of 1 and this is a length of 1, and that this vector and this vector are orthogonal to each other, right? So that's kind of the two ways of me going about this right now, is one, find A star, then also find A inverse and show that they're the same. Or I can verify this, that each vector is normal, right, a length of 1, and that these two vectors are orthogonal to each other. Okay, so let's go ahead and do that one, because I don't know, I feel maybe it's a little bit less work. Maybe it's the same amount of work, doesn't matter. A1, A2 is going to give me this vector dot product this vector. So if you notice, the first two terms I'm multiplying times each other, and then I'm adding that to the second terms. Remember, when you're doing the complex dot product, the values on the second vector are conjugated. So here I have 1/2 plus 1/2 I, and this has to be the complex conjugate. So I get the 1/2 plus 1/2 I. Here I have 1/2 minus 1/2 I. This needs to be conjugated as well. 1/2 minus 1/2 I. Okay. So when I do this, I'm going to get, this is perfect square. This is a perfect square. So if I square this is 1/4. If I square this is 1/4. And then multiply this and double it, gives me 1/4 times 2 is 1/2 times I. Same thing will happen here. You can verify this yourself. Okay. But I'll have a minus in the middle because I'm getting a minus 1/2 times 1/2 and doubling that. So the 1/2 plus 1/4 plus 1/4 is 1/2, minus another 1/2 from the end terms, and then the two middle I terms will cancel each other out, and you get 0. Okay. So the next thing I want to show is that the two column vectors are normal. Okay, so find the norm of A1. So this is going to be 1 plus 1/2 I times my second entry. Okay, 1 minus 1/2 I plus 1 minus 1/2 I times 1 plus 1/2 I. Okay. Also notice that this is a little different than the formula that I gave you, but it ends up being the same thing. So remember in the last video, I said you could just find the modulus of A1 and square it. So that would give you 1/2 squared plus 1/2 squared. And that will be the same thing for each term, right? So for the next one, it would be 1/2 squared plus a negative 1/2 squared. So you would have had a 1/4 plus 1/4 plus 1/4 plus 1/4. And when you multiply this out, you end up getting 1/4 plus 1/4 plus 1/4 plus 1/4 anyways, right? So this is your difference of squares. This is also a difference of squares, identical terms, different signs, and then you'll get an I squared, which will change the sign. So if you work this math out, you'll get this. If I were to take the elements from A1 and just take my A1 and square it, and my B1 and square it, I would get 1/4 plus 1/4. If I took my A2 and squared it and my B2 and squared it, I would still get a 1/4 and a 1/4, right? So that was our definition of the norm of a vector in complex vector space. So you can kind of do either one. So following that formula that I gave you in the last video will be the same here, or here will be the same thing, right? So square the first term, square the last term, and then change the sign because there'll be an I squared because the difference is squared. It's all the same thing. You get square root of 1, which is 1. So my length of A1 is 1. A2 is very similar. Apologies, this should 100% be A2 dot A2, so I'll change that in the write-up. But it'll be the same thing. 1/4 plus 1/4 plus 1/4 plus 1/4. So everything is the same. So the dot product between these, the complex dot product is 0, and the norm of each column vector is 1. So that's enough for me to show that it is unitary. Again, another way to have done that would have been to go through these steps here. And then I'm also going to show you another way that's even easier than this and this. Okay, so my columns of A are orthonormal because they are normalized and they are orthogonal to each other. Therefore, A is unitary. Okay. So diagonalize it. Oh, it looks like I skipped it. Sorry, guys. I guess I should just talk about it. I guess I must have skipped over it when I was writing out this lecture last night. Another way to show that this is unitary is to multiply A times A star. If you multiply A times A star, you should get out I, because since A star is A1, A times A star is the same as A times A inverse, which should get you I. Okay, so if you find A star and multiply it times A and get out the identity matrix, then your matrix is unitary. So that would have been another way of doing that, just through matrix multiplication. So find A star, take your A star and multiply it by A. It doesn't matter on the left or the right, and you should get out the identity. If you do that, that is an equivalent way of figuring out if something is unitary or not. Okay, so again, apologize that I did not get a chance to write that up for you. Okay, but it's an easy check, right? A times A star should be I. I know I did write it in that form later on, but I guess I didn't give you guys an example. Okay, so let's go into diagonalizing matrices. Okay, if A is a square complex matrix, then it is what we call unitarily diagonalizable if there is a diagonal matrix D and a unitary matrix P. So again, a unitary matrix is one that satisfies this condition, right? We just showed something was unitary. So if D is diagonal and P is unitary, then A equals PDP inverse. Okay, remember, what is P inverse? It's really just P star. Okay, so I can rewrite this as PDP star. Remember, this was our condition for diagonalizing a matrix. We had our QR factorization. We only had 2 matrices, but our Q was the same sort of deal, right? The transpose, we had the transpose instead of the inverse because the transpose and inverse was the same. So now instead of P inverse, I can just use P star. So once I find P, then I want to transpose it and take its conjugate, and that will be enough. I would not have to actually calculate the inverse in that case, which can be a big hassle, especially since we're going to have complex entries, right? So the diagonal entries of D are going to be my eigenvalues of A, like normal. My eigenvectors are going to form the columns of P. Okay, so everything really is identical to it was in the real vector space. It's just that now you have complex values you have to deal with. Okay, so a square complex matrix is called Hermitian if A is equal to A star. So this is the second important matrix we're going to work with. The first is unitary matrices. Those are important for us. Hermitian matrices are super important for us as well. Okay, so let's do an example of a Hermitian matrix. Here my diagonal is 1, 5. So when I take my transpose and my conjugation, those will stay the same, right? So notice that if I transpose this, sorry, let's just conjugate it first, right? If I conjugate this first, this will be 3 plus 2i, 3 minus 2i, and then after I transpose it, I will get back out my original matrix A. So A star is the same thing as if I were to do a transpose and transpose, and I just showed you that if I do that here, I will come back out with A, right? So if I change these signs, turn this to minus, turn this to plus, and then swap their entries, I'll get right back to where I was before, which is A. So this matrix, A star, is the same as A. So this matrix is Hermitian. Okay, so it's a little bit easier to check for Hermitians than it is unitary. Again, unitary, you want to check that A times A star gives you the identity. I think that's the easiest way. The way we showed before is a long way. It just verifies that it was an orthonormal matrix. Okay, and then if I want to check the Hermitian, I just take A star and it should be the same as A. So that's the quick ways to check both of these. Alright, so A is Hermitian since A star is A. So again, this is analogous to having a standard symmetric matrix in a real vector space that's n by n, right? So the things we can do to Hermitians are the same things we can do to symmetric matrices, right? So a Hermitian matrix must have real diagonal entries. Otherwise, when you take your complex conjugate, you wouldn't be able to get A back out, right? All Hermitian matrices are unitarily diagonalizable. Okay, so I can find a PDP star for any Hermitian matrix. Okay, so all unitarily diagonal matrices, however, are not Hermitian, so it doesn't go the other way. Okay, so just because I can find a PDP star does not mean that my matrix is Hermitian. Okay, so this is an important term. So again, this is that third set of matrices that we're interested in. So again, if A is n by n and complex, we call it normal if A star times A is the same as A times A star. So if A star and A commute with each other, it is a normal matrix. These are a very, very important set. These are our overarching set of important unitary matrices, right? Or in a unitary space, I should say. So all unitary matrices are normal. Okay. So remember, our definition of a unitary matrix is that A star is the same as A inverse. So here A star A is the same as A inverse A, which gets me out I, right? That's exactly what I was saying, is the easy way for us to check if something is unitary. But notice that if I break this A down in the opposite order, I can call it A times A inverse because it's A and its inverse. And since A star and A inverse are the same thing, you're going to get A inverse. So if you're in a unitary matrix, A star times A is the same thing as A times A star, right? So all unitary matrices have this property to be considered normal. So all unitary matrices are normal. That's a small direct proof right there to show that this is a true statement. Okay. All Hermitian matrices are normal. Okay. So again, I need A star times A to be A times A star. So A star times A, for a Hermitian, A and A star are the same. So A star A is the same as A times A, which is the same as A times A star, because A and A star are the same. A star and A are the same. So A star A is the same as A star. So all Hermitian matrices are going to be normal. Okay, so again, unitary matrices and Hermitian matrices, they don't have to be a subset of each other. Okay, I can have Hermitian matrices that are not unitary. I can have unitary matrices that are not Hermitian, but all unitary matrices are normal and all Hermitian matrices are normal. So the normal set of matrices are the big set of matrices that we are interested in. Okay, so I guess as an example, let's think about the number system. Okay, all integers are real numbers, right? And all quotients are real numbers. But then there are also numbers that are real numbers that are not quotients, or integers. So the real numbers is the bigger set that contains all of those things and extra stuff. That's what the normal set of matrices are. It's the bigger set of matrices. All unitary matrices are normal, and all Hermitian matrices are normal. And then there are other normal matrices that are not either of those, right? So that's what we're interested in right now, really, is normal matrices. Okay, so there are normal matrices that are not unitary nor Hermitian. The normal matrices is the bigger set. Okay, unitary and Hermitians, they are subsets of normal matrices. The normal set of matrices is the more important set. These are important subsets, however, that have, again, specific properties, right? Okay, so now that we got that out of the way, let's do one quick theorem and then an example, and then we're pretty much done, and that's it for the semester. You guys are finished. So the complex version of the spectral theorem. Okay, so remember, the spectral theorem was the theorem that allowed us to basically diagonalize things. Okay, so a complex matrix A is unitarily diagonalizable if and only if A is normal. This is why the normal matrices are important. Okay, so if you're unitary, you're unitarily diagonalizable. If you're Hermitian, you're unitarily diagonalizable, and that's because you're part of the normal set of matrices. If you're normal, you're unitarily diagonalizable. Okay, so this is the important theorem here. Super, super important theorem, right? 5 exclamation marks important. Okay, so here's a step to diagonalizing in the complex inner product spaces. First, we need to make sure we're normal. Okay, if we're Hermitian, automatically we're normal. If we're unitary, automatically we're normal. If we're not either of those, we just got to check that this holds true and that we are normal. Okay, we need to find the eigenvalues and eigenvectors of A. All of these steps are very standard. Okay, we're going to apply the Gram-Schmidt as needed for each distinct eigenvalue, right? So for no repeats, if I have 2, 2, 3, and 5 as eigenvalues, for 2, 3, and 5, I need to apply my... So applying the Gram-Schmidt here really just means make sure your vectors are normal, okay? Because default, they should be orthogonal to each other already. It's the normalization portion we need. We need each of those vectors to be normalized for my unitary P matrix in my PD P star, right? If my algebraic multiplicity, however, happens to be larger than my geometric multiplicity, so again, maybe I have an eigenvalue of 2 that shows up 3 times, but it only gives me 2 eigenvectors, right? I'm going to have to create my eigenspace basis by using the Gram-Schmidt for that eigenvalue, right? So I need to make a basis that's equivalent to the algebraic multiplicity, right? I can't have any missing things, right? So my eigenvectors of a normal matrix are orthogonal, okay? So this is a direct result from the real vector spaces that carries over to the complex vector spaces. So the eigenvectors are going to be orthogonal, and the combined orthonormal basis for each eigenspace that I'm creating are going to form an orthonormal basis for Cn, right? The n size vector space of complex entries. My D matrix is going to be diagonal, and it's going to have the entries of the eigenvalues of A, right? So same thing from before. And the last thing is P will be unitary, and it'll be made of the corresponding eigenvectors of A to these eigenvalues from D, right? So again, forming D and P there's really nothing different except that you have complex values. And before, when we had complex values, there was a shortcut that we did with the complex eigenvectors. We don't take that shortcut anymore. We use each eigenvector that we find. Okay, so before we were able to find one complex eigenvector, and we turn that into our P right away by looking at the real part and the imaginary part when we're looking at the complex ones. We don't do that here. Here we just form each individual eigenvector one at a time. Okay, so let's look at an example. So again, I know this looks like a lot for 3, but a lot of this verbiage is just to say that the eigenvectors that we get need to be normalized, and once they're normalized, they will form a basis, which we already know, and it'll be an orthonormal basis for each eigenspace. And then once we have those, once we put them together, that's why it will form a unitary matrix, because they will be orthonormal to each other. Okay, they'll be normalized and they'll be orthogonal to each other, right? So this is just saying that we can take those eigenvectors and put them and use them as the column vectors for P, and that will by default make it unitary because they'll be orthogonal to each other and normalized, right? That's what all of this is saying basically. And it's also saying if you run into problems, use Gram-Schmidt, right? So those are the steps. So let's do an example. Okay, let's diagonalize this 3 by 3. So again, I try to give you something a little more difficult than normal. So a 3 by 3 instead of a 2 by 2. So if you look, I have real diagonal entries. It looks, I have complex conjugates in the transpose positions. So it's very possible that this is, I don't know which one, Hermitian or Unitary. Which one has to do with A being same as A star? Is that Unitary matrix or Hermitian? If you guessed Hermitian, you're right. Okay, so let's check that. Okay, it's actually really easy to check. So if I take the transpose, positive, negative, positive, negative, or sorry, negative, positive, and then I transpose that. Did I just say that backwards? If I conjugate this and then transpose it, I will get the same thing as A, which means that A conjugate transpose is the same as A star, which means that this is Hermitian. And since it's Hermitian, it means it's normal, which means I can unitarily diagonalize it. Okay, so that's my first condition, right? Check if A is normal. Okay, it is, because A is the same as A star. Hermitian matrices are normal matrices. I'm good to go. Okay, I don't want to do all this if I can't even do it in the first place, right? There's no point in doing a lot of extra work. Okay, so if I want to find my characteristic polynomial, so first thing we're going to do is eigenvalues. Is next, right? So first is it normal. Next, find eigenvalues. So I'm going to find my determinant. So you guys know I like to do the 1, 2, 3, 4, 5 method. Here I'm just going to go ahead and do the standard what do you call it? Cofactor expansion method. So I'm going to start here and I'm just going to go down this this column just because I didn't want to start off with an imaginary, even though I would have zeros for one of these. I just didn't want to deal with it. So I'm going to start here. So positive, negative, positive, right? So I'm going to get, if this is my first one, these row and column go away, and I'm finding the determinant of this little submatrix. So lambda minus 2 times lambda minus 2 times lambda minus 2. So lambda minus 2 cubed. This turns negative, minus 1 over root 2i. So this column goes away, this row goes away. This entry and this entry give me nothing, so I'm really only interested in negative 1 over root 2i times lambda minus 2. My last one is positive, so I can keep it as a negative. Column and row disappear. Submatrix I'm interested in. This goes to 0 minus this thing, right? Minus 1 over root 2i, lambda minus 2. So pretty straightforward. Now if I multiply these crazy things in front, they're actually pretty easy. Negative and a negative is a positive. 1 over 2, because root 2 times root 2 is 2. So I have a positive 1 over 2. And then an I squared, which will make this negative. Same thing here. this will turn into a negative 1/2. So lambda minus 2 cubed minus 1/2, lambda minus 2 minus 1/2, lambda minus 2. I have two halves that are negative, so this will combine to be just a minus 1, lambda minus 2. Now I have a common factor of lambda minus 2 everywhere, so I can pull that out. And so, sorry, this should have said lambda cubed because I didn't do anything here. So this is a lambda cubed. I'll fix that in the write-up if I catch it after this. So I pulled out lambda minus 2. So this is lambda minus 2 squared minus 1. This factors very easily. Lambda squared minus 4 lambda plus 4 minus 1 will give me a plus 3 at the end. And now this factors very easy to a minus 3 minus 1 to give me minus 4 in the middle. So this is my factored form for the characteristic polynomial, which gives me lambda equals 1, 2, and 3, okay, in order from smallest to largest. So those are my eigenvalues. So the next thing I need to do then is find my eigenvectors, okay? So trying to keep this nice and organized for you guys, right? So that it's easy to follow since it's our last video. We'll go in order from 1, 2, 3. Lambda 1 equals 1. So again, I'm going to use this characteristic polynomial, put a 1 everywhere. So everything else will be the same, and I'll have minus 1 along the diagonal. Okay. Oops. Guess I didn't put a pause here. So I'll have this, and this is what I have. I know it looks terrible, but it's actually not that bad. I need to zero out these denominators. So R2 plus this thing, so because it's already got an opposite value, so that'll cancel them out. And then this one, I need to make it a minus so that it has the opposite value, so when I add them together, it cancels out. And then I just figure out what happens here for these values, okay? So just to walk you through it real fast, R2 will have a negative 1 plus 1 over root 2i times this thing. So I'm really just squaring it. It'll turn into a negative 1/2 times I squared. So this will actually turn into a plus. So I'm actually having negative 1 plus 1/2. This is going to be 0 minus 1/2. The same thing is pretty much going to happen down here. So all of these ugly things go away. So for my next line, obviously this row I can just get rid of. Let's normalize this one and turn them all into 1s because they're the same thing. So I don't know, I divide both sides by negative 2 or divide both sides by negative 1/2. Okay, it's really easy to see that this goes into that, right? So the last thing I want to do is I want to get this part to go away to 0 so I can put it into reduced form. So R1 will turn into R1 minus 1 over root 2i times R2. That's how I get rid of this. So by default, I know this will be 1, 0, something here, and these last two rows will stay the same. If you do the math, you get negative 2 divided by root 2. Because really what you're doing is you're taking another negative 1 over root 2 and you're adding it to this one, so you have 2 negative 1 over root 2i, so there's 2 of them. So that's going to give me x2 is negative x3, and x1 is a positive. If you simplify this and radicalize your denominator, it's really just root 2, right? You multiply this by root 2, you get 2 on the bottom, you get a root 2 on top, so this is 2 over 2, it cancels, and you're just left with the root 2. So this actually simplifies very nicely, and your eigenvector is 1, negative 1, I root 2. So x3 is 1, makes x2 negative 1. Plug in 1 here, you get I root 2, and that is your eigenvector. Okay. Lambda 2 is easier. You plug in 2 in your diagonal, so all your things turn to 0. That means immediately one of these can disappear to 0. This one you can turn into 1 because you just divide it by itself. And then maybe swap these two rows so that you have one in the pivot position. Okay. So I do that, and then I also just took these and divided it by 1 over root 2 also, because it's just a 1 over root 2 everywhere. I just divide everything by 1 over root 2. Everything goes to 1s, So reduced echelon form was super easy for this one. Just pull out that constant term that's everywhere, really, or divide by that constant term. So here I'm going to have x2 equals x3. My x1 is 0. I don't have to worry about it. Okay, x2 is x3. That gives me 1, 1, and 0 here. For lambda 3 equals 3, it's going to give me something almost identical to the first one, but instead of negative ones, it's going to be positive ones. So all of my work is just going to have opposite signs. I'm not going to go through this. You can go through it, on your own and verify it if you want to. But all the work I'm doing here is the same as what I did for lambda 1. Okay. In lambda 1, I had a plus 1/2 and I had a minus 1/2 here. And that's because my signs were different there, right? But I didn't know that when I did it. I did it by hand. It turns out that that's just the way it is, right? Okay. So everything that I have is really just the opposite value from before. But everything comes out almost identical. And that should make sense too, because if you notice x1 and x3, they're just complex conjugates. Okay. I have negative I root 2, I'm sorry. And look what I had here. I root 2, negative 1, 1. All of these matrices are the same. Just everything, instead of negative 1/2 everywhere, right, and a negative 2 root 2, okay, everything switches the signs, okay. Positive 2 root 2. It's all the same because they end up giving you complex conjugates because the diagonals are different. On lambda 1, all of these were negative, but everything else was the same. Here, everything is positive and everything else the same. It ends up just giving you that complex conjugate vector, which should make sense because that's how complex numbers work, right? So now I have my x1, my x2, my x3. Okay, I need to normalize each eigenvector so that I can have an orthonormal sort of basis of vectors, orthonormal column vectors, so I can make that unitary matrix P, right? So the first column vector for P is going to be x1 over the norm of x1, right? So normalizing x1. So first thing I need to do is find out what the norm of x1 is going to be. So again, I take the entries and I multiply by its complex conjugate and all that fancy stuff I need to do here. And I get square root of 2 plus 1 plus 1. So I get 2. Okay. So P1 is just going to be the entries that I had for P1, which again, lambda 1, x1 was the conjugate of this, right? So lambda 2 over 2i, negative 1/2, 1/2. So that means that x3 is easy to find. I just have the exact same thing because its length is going to be the same. The vector is almost identical, right? So P3 will just be the conjugate of P1 because x1 and x3 are complex conjugates of each other, right? So P2 I have to do separately. Remember that was 0, negative 1 over 1. So the length of x2 is root 2, divide everything by root 2. That was an easy one to find as well. So now I can find my P and my D and my P inverse. So P is P1, P2, P3. Okay, very easy. D is the order that they show up. So lambda 1 was for eigenvalue 1. Eigenvector 2 was for lambda equals 2. And eigenvector 3, right? This P3 was the normalized vector for my eigenvalue of value 3. Okay. P star is just the complex transpose of this, right? You notice this 1/2 and this negative root 2 over 2. They switch signs. They switch positions. This root 2 over 2 is positive instead of negative, right? Very easy to find P star once you have P. And remember, you always want to check. Okay, we don't know if this is right or not, right? So if I take this and multiply them across, I get this, which is my original matrix A. Okay. There's another quick thing we can do just to make sure we're on the right path, and that is my P and my P star. When I multiply these two together, I should get out the identity. Okay. If P times P star gives me I. That means that they are unitary. Okay, note that P times PI, P star equals I. So that means that P is unitary. I needed P to be a unitary matrix. So that's one way I can check to make sure I'm on the right path, right? Again, of course, I want to make sure that PDP star equals my original matrix. Okay. So last theorem is that if A is Hermitian, then A has real eigenvalues. So if you notice, our matrix A here was Hermitian, and my eigenvalues were 1, 2, and 3. Right? Even though I have a whole bunch of complex stuff going on in there. Right? So that's our last video. I hope you guys enjoyed it. You guys did well throughout this shelter-in-place transition, and I'm proud of you guys. So just keep studying. Do well on the final. Make sure you guys are just showing me that you understand how everything works, right? And everything will work out okay, right? I'll send up some follow-up emails later on. Thank you.